So let's begin. Introductions. Put this over here. Okay. In addition to being here, working for Red Hat at this point in time, I'm an author. I've written some books. I've done some teaching. Storage architect. Done a lot of work with storage systems. A lot of work with networking. I spent 10 years working for the University of Minnesota, designing and deploying both traditional data and storage networks. So that was a lot of time being on the user side and working with this kind of gear that we work with today to get some experience in how this all worked. Somewhere along the line, actually a long way along the line, I spent time learning as much as I could about SMB, about the SMB protocol, and kind of got to know a lot about it. I'm a Samba team member. I've been a Samba team member for 15 years. I keep remembering to slow down for the poor people in the booth there. 15 years. All of these documents that I've listed here, these three, okay, Microsoft has put out almost 500, maybe more than 500, but two of them are mine, plus this book, which is an open source book. It's freely available online. In fact, all of those documents can be downloaded for free. And that right there comprises everything that is really authoritative when it comes to the SMB protocol. The book covers, the basics of how to understand the protocol and implement it. And then those two documents are the specifications for what we now call SMB1. Okay? Now, that's kind of frightening in a way. I wrote everything that you need to know about, or that you have available to know about SMB1. And what that says is that that's one of the reasons you're here, is there's not enough knowledge of these protocols in the world. There needs to be more. And I would tell you that it frightens me that nobody else has written information at this level on SMB1. Thankfully, Microsoft has written this kind of information at this level for SMB2 and for all those 500 some odd other things that they've done. Okay? These days I work for Red Hat. I'm not here as a Red Hat person. I'm here for the Samba team. Opinions expressed are my own. The normal disclaimer we put on these things. They're not my companies. They're not my dogs. They aren't coming from the little voices in my head. So let's talk about what I want to talk about. I want to talk about what are our challenges implementing SMB, particularly implementing SMB on top of a distributed system. Metadata, semantics, behavior, how does that impact what we're going to do here? And semantic translation, explain what that means. I'll give an example using Samba, which is a product I work on. You notice that my slide template doesn't match the Microsoft slide template. I'm not with Microsoft either anymore. I was a contractor there for a while. We'll use Samba as an example. We will use the Gluster file system as an example. And then we'll get into some specific challenges that you'll face working on that kind of combination. And some of these, let me say, do apply to any implementation, whether it's on distributed storage or not. So here we go. Shakespeare, anybody know some Shakespeare? What's in a name? A rose by any other name would smell as sweet. One of my favorite movies, they changed that. Changed it just a little. A rose by any other name would wither and die. Subtle change, right? But subtle changes is what really get us. Okay? Subtle changes are where the problems lie. A name, a file name. One of the things that we face when we're working on implementing SMB is that file names differ. Okay? Windows rules for the maximum length of a file name path are different than the rules that Linux, Unix, AIX, some other operating system, BSD. They're different rules than those other systems use. All right? The set of characters that may be used in a Windows file name is different from the set of characters that may be used in a Unix file name. Windows always, nowadays, always stores both a long name. Okay, we don't do that in Unix. We just have a name. That's it. There are other issues that come up in the naming of files. And if you're not aware of those differences, they're going to cause you problems. You have to accommodate them. You have to make sure you understand how to translate one name into another. When I first joined the Samba team 15 years ago, one of the things I took on was rewriting a whole piece of Samba called name mangling. Name mangling. Name mangling is the whole process of translating a Unix name into something that is acceptable to Windows, and translating a Windows name that we receive into something that we can store on Unix. Okay? Usually Unix can do this because usually there are fewer rules in Unix when it comes to names, so usually Unix can handle the names. Names aren't the only thing that are associated with a file. Metadata, the data about data, the information about the file includes all sorts of things. Path name, on Unix it might be an inode number, timestamps, permissions, whole access control list system, file size versus allocation size, two different things, quota. And what's interesting about all of these bits of metadata is they all apply in different contexts. Some are specific to the file, some have to do with directories, some have to do with volumes. They're all interpreted in different contexts. Okay? They do all sorts of things. Provide state information, they set limits. And once you have this metadata, you have to apply meaning to it. That's the semantics, the meaning of the metadata. What does it mean if the size of a file is 512? 512 what? Usually it's bytes. But I remember file systems where it wasn't measured in bytes. Okay? Old times. So there's meaning to these values that are stored as metadata. And you have to be able to interpret that meaning. And your interpretation must not lead to conflicts. And it must be consistent. Behavior. One of the things I want to say, and I know this may be, I'm halfway around the world from my home, but I like it when people laugh at me. So go ahead. Those are my kids, by the way. They are misbehaving. So that's why I'm putting it on this slide. Behavior. Predictable outcomes. The semantic rules, such as how the access control lists are interpreted and enforced. Quota limits, how are they enforced? These are usually enforced by the operating system in conjunction with the file system. The two pieces work together to enforce the rules that are set by the metadata. And the actions that they take, the behaviors that you see, are based on the semantics of the metadata, and they must be predictable. And this becomes important when you've got a server and a client, and the client asks the server to do something, and the results come back, and it's not what the client expects. It's not within the set of things the client expects. We're just looking at a little bug in the other room. We had a bug in our server. When we asked it to do something it wasn't supposed to do, it sent back an error message. But it sent back an error message that was different than the error message that Windows would send back. And that's a bug, right? Well, we think it's a bug. Depends on how well Windows handles a different error message. The fact is that we should be sending back in the same situation, we should be sending back the same error message, same error code. And this is where the dragons are for the implementers. This is where it gets dangerous. All right? These differences, these subtle behavioral changes have a big impact We've been known in the 20 years that Samba has been developed. You know, we've had situations where we send back the wrong thing and Windows goes blue screen of death. You don't want that, right? We've also had situations where our clients, the SMB client tool, for example, will send a request and the server will say, I don't know what you're talking about. Well, that request works against 5 or 6 other servers, but this new server doesn't work. That's an unexpected behavior, okay? And those are the things you have to be aware of. Now, in that particular case, I won't name names, Apple, but that particular case, you're supposed to laugh at that one. In that particular case, the vendor writing the server said, that command is only sent by old Windows machines, and we're not going to support the older Windows machines, except that it was sent not just by older Windows machines, but also by the SMB client tool. So whose bug is it now? Whose bug is it? Very interesting question, too. Here are some. This is a partial list. Here are some of the areas where you will find that it is difficult to create agreement between a Windows system and a POSIX system. Okay? The behaviors are different. The fact that the behavior exists may be different. Right? Different types of behaviors are generated from these particular features. All these slides will be available, so you should be able to get hold of these pictures. So semantic translation. Semantic translation is the general idea of taking one set of behaviors that are expected, one set of semantics from one system, and translating them somehow so they can be managed and handled on another system, and then translating that back so that the answer you send to the original is something the original client can understand. Okay? And the example I'll give is Samba. All right? Most of Samba is a semantic translator. It's a semantic translator engine. It takes the client's expected Windows, the client's, sorry, start again. It takes the Windows request the client makes, the Windows semantics from the client, translates them into POSIX, does the job in POSIX, whatever that job is, translate the result back to Windows and sends it back to the client. Okay, this is not usual. I'm not usually putting people to sleep. But pieces have to fit. If Samba does not properly handle something, an SMB request, if Samba doesn't know how to deal with an SMB request, we call that a bug, right? That's a bug. That's a problem, okay? But if the file system doesn't properly handle a POSIX request, that's also a bug from Samba's point of view. And when we start talking about the distributed file systems, Ceph, Gluster, and a few others that are out there, there's Moose, there's a few cluster file systems, GPFS, GFS2, several others that people are developing right now. All these things going on, all right? Some of them, in order to work in a distributed or clustered environment, play loose with the POSIX rules and don't give Samba the responses it expects. Typical areas of trouble, byte range locks. You set a byte range lock on a piece of a file on one node of a cluster. Do you immediately get that lock on all nodes of the cluster? Do the other clients talking to other nodes of the cluster see that byte range lock right away? Do they? Very important, right? Okay, so the general approach we use in Samba is one of emulation and adaptation. We do both things at once. We use our own internal metadata store in order to emulate and enforce the expected Windows behaviors and metadata, right? we store the metadata, the Windows metadata, and we enforce that metadata. That's the semantics within Samba. We do this all within Samba. And I'll explain how we do that in a moment. Adaptation. In addition to having to take care of the Windows semantics, we also have to play well with the other processes, the other processes that are running on the same server. So let's say there's an NFS server on the same directory. Let's say there's a local process, a program running that's using files in that directory on the local machine. We have to accommodate those, which means we have to play by the POSIX rules. Okay? So we do both. One example that's near and dear to our hearts. My friends in the back going, ah. All right. NTFS ACLs, Windows ACLs, access control lists. An access control list is made up of access control entries. Each entry says, given this ID, here's what they may do or may not do. Okay? We can convert a Windows ACL into a POSIX ACL. We can do that. The problem is it's not a perfect conversion. We lose information in the process. All right? And I see. Oh, is talking to Justin here, and I'll talk about the A-time example too. But the problem is we lose information, which means that when the client sets an ACL on a file, and then comes back a minute later and says, "Show me that ACL," it'll come back different if we just do this. It comes back looking different because things have changed. Move that up a little bit. There we go. Things have changed, right? So the user notices this. This is a problem for the user. So what we do is that we actually take the entire Windows ACL, and in addition to storing it as a POSIX ACL, converting it and storing it that way, we also take the original Windows ACL and we put it into an extended attribute in the file system. If we don't have extended attributes, we can use the database. If we don't have either, we give up. But otherwise, we store the entire Windows ACL in an extended attribute. That way, when Samba gets shut down and a week later gets brought up, the ACL is still there. It's still part of the file. Okay? And then, when we're running as Samba and the user wants to connect, open a file, right? We first use the POSIX ACL to make sure we're allowed to have it. Otherwise, we'd be breaking the POSIX rules. Then we check the Windows ACL to see if Windows would also allow us to use that file. Actually, the order we do this is the opposite. We do the NT1 first because it's faster. We check that first, then we do the POSIX. In either case, we check both. We check both to enforce the rules of both systems on that file. And this is an interesting problem because what if somebody came along, we're running Samba, somebody sets an ACL, we shut down Samba for a week. While it's shut down, somebody comes along and sets an NFS v4 ACL on the file. NFS has its own ACLs too, just like SMB does. So you can set a different ACL, and that ACL has changed the rules now. All right? You start up again, and the Windows user wouldn't know how to interpret. Well, why can't I access that file? So we have to take the POSIX ACLs, the NFS v4 ACLs, and the Windows NT ACLs. Too many acronyms. Sorry. We have to take all those sets of ACLs and combine them together and give the user the result. This is what it is now. It changed. This is what it is now. All right? And in this case, when we're storing the NT ACLs in a POSIX extended attribute, it's Samba, not the operating system or the file system, that has to enforce the Windows ACLs. Okay? Those are birds. And that's a fish. Officially. Samba on Gluster. All right? So to continue my example, using Samba, I will also use the Gluster file system, which is something that I've now learned to work with, thanks to my friends here in the audience, who, by the way, should throw things at me if I get something wrong going forward, okay? In very simple terms, I use the term cluster loosely. A cluster means a bunch of nodes providing the same service together, okay? But there's a subtle distinction I want to make between a cluster file system and a distributed file system. In general, Gluster is not a cluster file system. In general, clusters use a shared block level device to store their data. All of the nodes in the cluster have access to the same blocks, okay? This is a broad generalization, but it gets the idea across, all right? What Gluster is a distributed file system. In the cluster, each node has its own separate private storage. And Gluster then uses each piece of storage to build a distributed data set based on files, not blocks. Okay? So two of those nodes here. Let's say this node here and this node here will have directories on their storage. And those directories, we call them bricks. I'll show that in a moment. I've got a slide on that. But those directories, we call them bricks, and we can combine them together to make one volume. And one volume is a virtual directory. It really spans two servers, but it's one directory. Okay? I need one of those remote control mouses. That's what I need. I actually have one, but I didn't think to bring it in here. So Gluster being a distributed file system, we generally have a front-end network, typically a back-end network. Correct me if I'm wrong. Each node provides these bricks. Each brick is really a directory. The bricks are bound together as volumes, and the volumes are distributed and or replicated. That means, I described before, there's one directory, it's really two directories on two disks. The other way we can do it is we can replicate things. Ah, look at that. Right. Now, I'd have to do this. All right, let's see if this works. Woo-hoo. Aha. Ooh. Oh, it does work. Thank you very much. All right. So the volumes can either be distributed or replicated. Replicated means duplicated. They're copied to another volume, and not another volume, pardon me, another disk on another node. That way, if one of the nodes goes down, there's still a live copy of all the data that was there. Okay? So we can do both in Gluster. But then once we put all this together, we then have to make it available to the world, right? So how do we do that? We have a set of what are called access methods. And access methods are quite simply NFS, SMB, fuse, what else? Give me some more. Okay, there's a library, libgf API, and UFO, which is a REST architecture. Yeah, okay. So we have a variety of different ways to get to the data, to read it and write it, depending on the kind of things you want to do. We have a Swift interface. We have OpenStack we can run on top of this. There are a few other things we can do with it. Now let's switch gears and go back to Samba. Samba is built conceptually in layers. It's really a little more complicated than that. But basically, Samba is built in layers. At the top layer, we have to be able to parse the SMB protocol, right? We need to know what the SMB protocol is doing. So we parse that apart. And then we hand it to another layer, which makes sure that the information we're getting is correct and clean and works and makes sense. Okay? Then, once we've got clean, scrubbed, nice data, we pass it to our VFS layer. Within Samba, which runs in user space, within Samba we have a virtual file system layer. And it's basically a set of function calls that have to, you have specified inputs to these function calls, and you have a specified set of outputs. That makes it an API, right? A programmer's interface. And the nice thing about the VFS layer is it can stack. You can build a VFS module, and then you can put another one on top of it. And then you can put another one on top of it, and another one on top of it, so that when the call comes, it goes to the top level VFS module. If that one doesn't know how to do anything with it, it passes to the next level. Maybe that next level modifies it a bit, passes it to the next level. And eventually, at the bottom of the stack, you get one called the default VFS layer. The default VFS layer is actually in the Samba code. You can find it. It's in source 3 / modules, and it's really called default. And default is a POSIX interface. It expects from the actual file system here, it expects POSIX behaviors. And this is the problem I discussed before. What if your file system doesn't quite do POSIX right? Okay? So what we've done, VFS allows us to adapt Samba to behaviors of underlying file systems, because we can now, in a VFS module, we can adapt the behavior of the file system to what we need for SMB. Right? We can work around bugs. We can bypass limitations. We can take advantages of cool features in the file system. So if you have a cool new file system you've created, there's some modular file system that does amazing things, you can take advantage of the features of that file system at this layer. You can tune for speed here. We've done this a couple of times to bypass problems that we would otherwise have. We have ways of caching things and translating things right there in that layer. And so putting the pieces together, Gluster provides a client library, which Tulor was telling us, libgf API. With that library, we have a Samba VFS module called VFS_GlusterFS. It speaks directly to libgf API. It's a client. libgf API in turn talks to the Gluster server, the cluster itself. It'll pick one of the servers in the cluster and it'll talk to that, and maybe that one will forward, maybe that one will forward the request to another node in the cluster. But basically, we're now talking over a protocol from Samba to Gluster directly. And this is nice because before we created this, what we did was we took the Gluster file system, we did a fuse mount. If you're familiar with Linux, you know about fuse mounts. You can mount a user space file system. And we'd mount it that way and then run Samba on top of that, going through the default VFS to talk to fuse, to talk back into the kernel, back out of the kernel, to talk to Gluster, and then back in and out again. It was too many kernel transitions. We got rid of a bunch of them by doing it this way. This is, by the way, the right way to do things with Samba. Samba expects that if you want to talk to a file system in a special way, if you don't want to just use the default POSIX behavior, and you want to talk to a file system in a special way, what you're supposed to do is use a VFS module. Write your own VFS module for Samba. Okay? All right. So now we know how Samba talks to Gluster. And I'm having all sorts of popping noises here with this microphone. Are we okay? Is it okay? All right. I want to make sure the folks in the booth are okay with it, right? Okay. We've talked about how we get Samba working on top of Gluster, but we've got one more problem to solve, and that is Gluster has many nodes, right? It's a cluster of systems, so there are multiple nodes there. So Samba has all this metadata it's maintaining itself, right? So how do we make sure that that metadata is synchronized across all the nodes in the cluster? And the answer is this thing called CTDB, Cluster Trivial Database. Okay? There are three basic services that CTDB offers. CTDB is a part of, it's shipped with Samba. It's an extra piece. You compile it, you tell Samba to use it, and it does. First of all and foremost, the most important part of CTDB is that it is a metadata database. That means it maintains that special emulation database that we have to keep in Samba. The one I showed you, let's go back. Come on, go back. There, store and force. We have to keep our own data for that, right? Okay, so when we can't use the file system, when we cannot use the file system to store the information, for example, if we can't use an extended attribute to store the information we need, the extra information we need, then we use CTDB. It is a distributed database. Okay? The other things that CTDB does for us is it has its own heartbeat. It listens to the cluster as a whole. And if it detects that a node in the cluster has gone down, it does recovery. Or if it detects that a new node in the cluster has arrived, come back up, it does recovery. It makes sure that everybody has a consistent view of the data. All right? IP address service failover. When a node goes down, CTDB takes the IP address that that node was using for services, for providing services, and it transfers that IP address to another node so that the clients can continue to operate. Okay? That works really well with NFS. We'll talk about SMB in a moment. Okay? Basically, though, it synchronizes the Samba servers running on each of the cluster nodes. It makes sure that each of the Samba instances running on the cluster nodes is in the same, knows what the other ones are doing. It shares the data between them. And it does it in some pretty cool ways. It's pretty fast. But there is a bit of a problem here. And that is that we've already got a cluster created by the Gluster software, right? And then on top of Gluster, each of the nodes in our cluster is running Samba. And then on top of Samba, we have CTDB creating a cluster. So the problem is we have two cluster systems running on the same cluster, and they don't always synchronize with each other. So CTDB doesn't really talk to Gluster, and Gluster doesn't really talk to CTDB. And there's some subtle problems that come up there. One of the biggest really is redundancy. You have the same things happening at two levels. Heartbeat, failover control, things like this are happening at multiple levels, and they have to be coordinated for the cluster to run properly, and sometimes they're not so well coordinated. And that's a problem we're looking into. We have some ideas on how to fix that. That's the sky over Minnesota. Not today, but a while back. All right. So let's talk about some specific SMB challenges. Okay? SMB challenges on distributed and clustered file system. She's not happy. All right. One of the main things about SMB1, the older version of SMB, is that it really was not designed for clustering at all. Now, we got around that in Samba. We were able to do scale-out clustering. CTDB made that possible. You could have 5 servers serving the same data, whether it's a cluster file system or a distributed file system. You could have the same server, you could have all 5 servers serving the same data, and that would do scale-out. That would let you have multiple clients connected to different servers all seeing the same data. That part works nicely. But when an SMB client detects that a TCP connection with the server has dropped, it drops all of its state on the ground, and the server does too. The client gives up. It says, the server's gone, I panic, I lose, I'm gone. I have seen these things happen. Blue screen of death, application crash, application freeze, application give you an error message saying something's wrong here and exit politely. Application say, hang on a minute, and actually recover. But notice I keep saying application. It's not the OS, because the file system, the SMB file system on the client, doesn't know how to do recovery. So the application may say, okay, wait a minute. Let's retry the connection. Maybe it'll go to another server. Maybe we can pick up where we left off. Maybe we can figure out what went wrong and go from there. A well-written application may do that. But a poorly written application, or actually, honestly, your average application, is not going to expect that the file system just disappears out from under it, right? This just doesn't generally happen. But it can happen in an SMB world. So it's the SMB1 protocol itself that really doesn't allow scale-out or failover. Scale-out we can do because we can trick it. We can fool it. There's no real need to tell the protocol that we're doing this. Okay? Now, when we got to SMB2, people started really thinking about this stuff. I remember when the folks from Microsoft first showed up at one of our Samba conferences. Every year in Germany, we hold a conference for Samba called Samba XP. I think it's called XP because we're trying to be silly. But Samba XP, and it's usually in May of every year. It's in the North German town of Göttingen, which is, by the way, very pretty town. Nice place to go visit. Microsoft showed up at this, I think the first time was 2007 or 2008. I don't remember when. And they kind of went back home going, they're doing clustering. What the heck? What's that? And so with SMB 2, they'd already added something called durable handles. This came out with Windows Vista. Durable handles are resilient against a loss of network. So if the client and the server are talking, but the network goes down, all right, like that, all right, and then comes back up. Oh, I'm back. The server and the client and the server still have the state they had before. They can reestablish their TCP connection. They can talk to each other and say, hey, you okay? Yeah, you okay? Yeah, okay. Can we pick up where we left off? Yeah, we can. All right. And they can reestablish the connection they had. That's durable handles. But starting with SMB3, they got really fancy with durable handles. And they called them persistent handles. And now, what the server does in a cluster is, in addition to keeping its state, it shares its state with other nodes in the cluster. And that means that if that server node goes down, the other nodes in the cluster are in a position where they can take over. The client says, hey, you there? And another node says, yeah, I'm here. And the client says, well, this is how far I think we got. And the server says, I only got this far. And the client says, okay, I'll replay the missing transactions, the missing requests. All right? And so there's a moment's delay as the client fails over to a new server, but the server has got enough information, the client has enough information, they can pick up where they left off, they can recover and keep going. And that is the first instance of failover support that we really have in SMB. Okay? The SMB protocol provides that. In addition to that capability, there's also something now called the witness protocol, which does two things. First of all, it monitors the network, sort of like CTDB monitors the network, and detects when a cluster node has failed. And it tells all the nodes, all the clients of that cluster node, hey guys, change to another node. All right? The other thing it does is if the administrator comes along and says, hey, I want to shut down node number 3, the administrator can tell, via the witness protocol, the administrator can tell all of the clients, correct me if I'm wrong, but the administrator can tell all of the clients that are of node number 3 is going to go down, find another node, tell them where to go to find another node, and boom, all of a sudden there are no clients on node number 3. You can take it down without disrupting anything. Controlled failover. And this is the first dialect. SMB3 is the first dialect to support any of this. But in this environment, we need to consider the challenges that we're going to face. All right? How do we implement some of these features? For example, that persistent handle. How do we make sure that we transfer the state of that persistent handle to all of the other nodes in our cluster? So if one node goes down, somebody else can take over. Okay? How do we make sure we're maintaining like a log or a what's the term they use in ext4 and XFS? A journal. A journal. Okay? Journaling file systems. How do we maintain a journal so that we can keep track of what it is that we've accomplished on the server side, so when the client reconnects to a new server, the new server can say, this is where I am. And then they can replay the missing pieces. When we do failover, it's not enough to say, well, we're going to fail over the share, we're going to fail over the file handles. We also have to make sure we do things like fail over the authentication context. And that's one that, people sometimes they miss. Oh, we can do this, we can do this, we can do it. What about the authentication context? We have to log in again? Well, we do. Essentially, we have to do some sort of a login on the new server. But the point is that any node in the cluster really should be able to accept a failover from any other node at any given time. More challenges to consider. When you're building a system like this, we have clients talking to a group of servers, right? And the purpose of it is to make sure that we're isolating the load so that one client talking to one server is making that one server do some work, but no others. Except that in a distributed file system, you've got the problem that maybe the data you want isn't on that node. So now that server node has to talk to another server node, and now both server nodes are doing some work to service the one client. And particularly if you have clients for the same file, let's say, that are connected to nodes across your cluster. It's much more effective if, for any given file, the clients dealing with that file are all talking to the same server. And other clients dealing with other files are talking to other servers. Right? That would be the best. But in a distributed system, you can't do that. And in a cluster system, you also have a problem. Because even though every node can access the same blocks, the locking has to be distributed. And that means that if this node in your cluster and this node in your cluster are both trying to access blocks belonging to the same file, they have to be talking to each other all the time. Are you writing now? Are you writing now? Are you writing now? Are you writing now? And another thing is the order of writes is significant. You can't just randomly change the order that the writes come in. They need to be applied in the correct order. All right. So these are issues of distribution versus localization on locality on your cluster. Here's an interesting one, and this is one I know Microsoft has an answer to. They've got a cool mechanism of doing some of this. Copy offload. One of the things that SMB3 does, SMB2, SMB3, is it allows you to say, I want to copy this file from here to here, or I want to move this file from here to here, and then let the server do it. And the server will come back and send you a message when it's done. Finished. Now this beats the old way of doing it. In SMB1, if you wanted to copy a file from here to here, same server, different directory, maybe a different share, you had to copy each block and then copy it back. So the entire file went down to the client and back to the server to do a copy. Okay? That was slow and annoying. Slow and annoying. But Windows now supports copy offload, where you tell the server, that file over there, I would like a copy of it in this location over here on the same server. And I think they can now do, Brian, can you now do to another server using backend if it's on the same storage, or is that not yet done? Yeah, so they even have a method for multiple servers here.
That relies on the adapter.
Right. Right. So the intelligent storage has to be able to do the work. So basically, yeah, there's all sorts of things you can do with copy offload. In a cluster environment, how are you going to handle that? How are you going to make sure you've implemented that correctly so that you have the best ability to make those copies quickly? Locking, I think I mentioned before, op locks and leases, same thing. They have to be cluster-wide. They have to be cluster-wide, except that maybe there are ways to fudge that. There's some interesting things you could do by saying, I'm going to just lock the file uniquely here, exclusive lock, and then you can give off different kinds of locks to just the clients on that node. There's some games you could play. And I don't know, I thought I had a lot of time to take up. The last time I gave this presentation, it took hours, didn't it? But I had a lot of questions thrown at me during the whole conversation. So I think instead we'll have all the questions now, and I hope there are some. What I've hopefully done here is given you some overview of the different problems people face, and particularly problems in a distributed environment. But you know, this presentation is fairly open. If you've got anything, you know, there are people from Microsoft here too who will help. But if you've got any questions about how you would implement a piece of this, or what the specific problems might be. Let's, please. No? Everybody's quiet? Okay. We get a long break then. But I'll be in the testing room next door if anybody has any more that they want to ask me. And that's the end. Thank you.